Hello everyone. So I am here to talk about CONCURRENT-RUBY and the new framework which is in CONCURRENT-RUBY version 1.1, or it will be because I didn't have enough free time before the conference, so I decided to rather postpone it after the conference than rush it, so it will be out in the next week. So my name is Petr Chalupa. I work for Oracle Labs, which is a research group within Oracle. And amongst other things, we also work on a new Ruby implementation called Throttling-RUBY. I'm just curious, who heard about Throttling-RUBY or previously called JRuby? Wow, okay. Who didn't, you can look up this video from last Ruby conference. And there is also a status update after the 27th minute. But I'm not here today as an Oracle employee. I'm here today as a maintainer of CONCURRENT-RUBY, so I'll be talking about that. So CONCURRENT-RUBY is not a new Ruby implementation. It doesn't also have any language extensions. It's a Ruby gem. It exists since 2013. And it's basically an unopinionated toolbox of tools, so you can pick up abstraction based on what's your problem, so you can pick the one which suits your needs best. So it's a collection of low-level abstractions and high-level abstractions. We don't have any dependencies because we don't want to try, we don't want to create problems with dependencies. We are Ruby implementation independent, so CONCURRENT-RUBY runs on CRuby, JRuby, RubyNews, and Throttling-RUBY. It's open source. We have about 3,000 starts, and currently about 207 gems depends directly on this CONCURRENT-RUBY. And some of the major ones like Sucker Punch, Sidekick, Rails, Hanami, Dry, RB. So let me say a few words about the current state in Ruby world about concurrency. So the CRuby implementation is the only one which has a global interpreter lock, so it doesn't have true parallelism, only JRuby, Throttling-RUBY, and RubyNews. And the only tools which we have available are thread, queue, mutex, monitor, and condition variable from standard library. Which is not much. There are also a few tools available which are Ruby implementation specific, like JRuby synchronized, RubyNews channels, and log, but that's not portable, so it's not good either. We also don't have any volatile variables or anything like that, so we always have to use mutexes and logs. If you oftenly used solution when you want to true parallelism but you want to run on MRI, you start forking, which is not optimal either because you cannot do that on JRuby, so you have to do different things if you want to migrate and stuff like that. And also it's not very easy to deal with locking and with mutexes and threads. So we try to improve this situation with CONCURRENT-RUBY. So CONCURRENT-RUBY is really 3 gems. The first one is the core, which is the stable core, which also includes all the Java extensions, because there is never any problem with them, because they are compiled before they are downloaded to your computer. Then there is also CONCURRENT-RUBY Edge gem, which contains some experiments and new abstractions we are adding. And after that's stabilized, it goes to core, which is what is happening now with the new Promises framework, which is the main topic of this talk. And the third one is CONCURRENT-RUBY extensions, which provides all the C extensions. So usually you just also use the CONCURRENT-RUBY ext, and only if you have some problems with compilations, you can drop it and still use CONCURRENT-RUBY. So the gem includes a lot of things. I won't go. We have lots of high-level abstractions, some atomics, synchronization primitives, and other tools. So if you have a problem, it's probably a good idea to look into CONCURRENT-RUBY if you find what you need. But let's talk about promises now. So who knows promises from JavaScript? Yeah, pretty much everybody. Okay, so this framework is basically, it's a superset. It has more things and just JavaScript promises. but you get a good idea from that what this is. So it integrates previous abstractions we had: future, promise, IVAR, event, data flow, a delay, into one tool. So you don't have problems with convention between the classes anymore and compatibility and stuff like that. And uses the names from JavaScript, so it's more familiar. So what's new about it? It uses the synchronization layer with built-in concurrent-RUBY, which basically provides the volatile variables and compare and set operations on those variables. So it allows us to build this framework, these promises, with just compare and set operations. So we've avoided using mutex, so it's much faster because we don't have to lock anything for most of the operations, with the exception of obviously blocking operations like value and if you want to wait on the promise. But also it integrates with other abstractions. So if you use these promises, you are not limited to just using promises. You can combine it with actors, channels, and processing actors, and I'll be talking about that more. So this is basically the outline. I will go through the basics of futures, how to chain them, branching, zipping, and so on. So the main classes in this framework is event and future. The first one represents just some event which will happen in the future. It doesn't have any value or anything. It just allows you to have an object which represents some event which not yet happened. And the second class is future, which we'll be talking much more about. And it represents a value which is not yet computed, and it will be available sometime in the future. So the event has two basic states. It's either pending or resolved. And the future is pending or fulfilled and rejected, where the fulfilled and rejected basically mean that it's resolved. So for event, there's a bunch of convenience methods, so you can figure out what state it is in. After the event is resolved, you can obviously check that it's resolved. For future, you have two more methods to tell you if it's fulfilled or not. And if you fulfill the future with some value, you obviously get change state, and you can read the value from the future. The future also can be rejected if it's constructed with some error. So then you get you can get the error out of the future with the reason method. So let's have a look at an example of what the event is good for. So we will have two threads, and on the first one we call some long calculation foo, and on the second thread we have a method which is depending on this foo calculation. I want to synchronize the two threads to ensure that the second one, your dependent method, is called only after the first one finishes. So we can construct with this factory method on promises module the event. Then we create the first thread, we run the first method, and after that we resolve the event. The second thread, meanwhile, also starts, and it will wait here on the event. It will be blocked on this line until the event is resolved, and then it will continue with calling the method dependent on foo. But often, you usually want to communicate also some results from one thread to another. So for that case, if you create a resolvable future instead of event, you can, instead of just resolving an event, you can fulfill the future with the result of the long calculation foo. And if you do that, you can then read the value out of the future on the second thread. This is again a blocking call, so the thread will be blocked here until the result is available, and then it will be passed as an argument to the foo dependent calculation. But of course, we want to get away from working with threads. So we can use a different factory method, which is the basic one for doing asynchronous operations with this framework. So you just call a future factory method, and this block will be immediately start to be evaluated on a thread pool asynchronously. So we don't have to create a thread for the to call the long calculation foo. But of course, we want to also get rid of the second thread as well. So for that, we can use chaining. So after we construct the first future, we can call then on it, which is a second future, which will be called immediately after the first one fulfills with the result of the long calculation foo. One warning. It's not really thread safe to pass arguments to these blocks through capturing the local variables. Because if the local variables are changed later, there is no really any locking, so on JRuby and other implementations it can break. So as you should do with threads, passing the arguments directly through the constructor, the same thing should be done with promises. So you should pass the arguments through the factory methods or through the chaining methods. But of course, you are not limited to constructing just chains of the futures. You can branch them as well. So if you have a head future, which is the first one, you can construct two branches which will be evaluated in parallel. And later, if you need to combine the results together again, you can zip the futures together, which is just another constructor which gives you another future which represents the result of both futures. So it will give you an array with values of the first future and the second future. This is just the different syntax for that. And you can also take only the first evaluated or the first resolved future. So for example, if you have two parallel computations and you want just the first one, you can use any. So the simple use case for this is that, for example, if you have 4 parallel tasks and you just want to wait until all of them are computed, you create this example. We have the 4 tasks represented as a procs. We construct 4 futures, and then we zip all the futures together, which will give us another future, which represents all 4 results. And we can then pick up the result with the value method to get all 4 values. It also sometimes happens that you end up with nested futures, which is fine, but you have to avoid using this naive solution where you would call a value method inside the future, because this is a blocking call, which means that in this case you would block the thread which is currently evaluating the outer future, which if you have enough of them could starve your thread pool. So it's not really effective. So there's a better solution. You just call a flat method on the outer future, which gives you another future which will be fulfilled with the value from the inner future. So this will just get you the result of the inner future. And this is implemented in a way that it doesn't break any thread. Another requirement is often is that you need some lazy computations. You want to wrap some evaluation for later. So if you construct a future with a delay factory method instead of future, this future won't start evaluating immediately, but will start only when you call value or wait on the future. But those are blocking calls, so if you want to avoid the blocking, you can also use touch method, which just makes the future evaluate its block. And you can also insert the delay inside the chain of futures. So in this chain, it first creates the first future. That one will start evaluating. The second one chain, the succession will be called also. Then it creates a lazy future, so it will stop there until you ask for the final result. So if you ask for anything, there can be another 3 futures chained. Doesn't matter if you ask at the end, it will propagate, find the lazy future, and it will evaluate. when you need it. Another requirement is scheduling. You often need to run some code asynchronously at a certain time or with some delay. So for that, there is a schedule factory method. So this one will just call its block in 1/100th of a second, and then it gets fulfilled with the result. Again, this can be used in the chain as well. So you can have a chain which is evaluating the futures, then it will insert some delay if you want to, or you can also pass a time to it, so it will wait until, I don't know, 4 o'clock. Another thing which was missing in CONCURRENT-RUBY for some time was some way for canceling the tasks. So we've added cooperative cancellation. So it requires that the programmers, the users, check that the cancellation is still valid or that it's not cancelled. But on the other hand, this doesn't require any threads, or it doesn't blow up your application like timeout can, because if timeout works, that it creates another thread, and when it times out, it raises exception on your production or application thread, and it can happen anytime, including rescue blocks, and so it can abort your commit to a database or anything like something like that. And this is not limited just to promises. This cancellation, you can use it with actors, channels, threads, whatever. So in this example, we will have 4 futures, which will be just trying to calculate to 1000. And they will be randomly failing. If one of them fails, it will cancel all the others. So at the beginning, we create a cancellation, and that will give us 2 objects. The first one is source, which is the source of the cancellation, which is the only object you can cancel this cancellation. And the second one is token, which is for you to pass around to different objects, where you can check if it's still not cancelled. So if you have a look inside the block, the first thing it does is that it checks that the token is not cancelled. If it is, it just breaks and cancels the future with the cancelled symbol. If it's okay, it continues, and there is the random failure. If it fails, it cancels using the source and raises an exception, then it does some stuff, and then it repeats. As you can see, if we zip all the tasks together, I've used a result here which returns a triplet of if it was fulfilled, then the value of the future, and then the reason of the future. So this one was rejected because one of the futures failed. The first 3 ended up with the value cancelled, and the last one failed, and in this case, the first step. You also often need some way of throttling concurrency. So if you have, for example, some limited resources or something like a database, which is simulated in this example with this thread-safe array, then you need a way how to ensure that if you have, I don't know, 100 chains, that certain tasks in the chains are executed only 3 of them at maximum at the same time. So in this case, or for that, you need to create a throttle with the limit. Then in this example, we have 10 futures, and we start constructing them by using a factory method on the max tree, which is the throttle. And this gives us futures which will be limited to evaluating only 3 at any given time. Because it returns future, you can again chain anything you want and after that. So the second future chained, these will run in a full without any limits. So 10 at the same time, for example. We also have actors. We actually have 2 implementations of actors at the moment. The actors, this is the older one, which is similar to akka. which means that the actor is evaluating when the actor gets a message, it's processed by calling a method, which means that the actor doesn't have any stack. You have to maintain where you are in the actor by yourself. So usually you also build some kind of state machine in the actor to remember where you ended up after processing previous message. Because the promises don't really have any state, it's just represent some evaluation. The actors are good when you need to maintain some state. So for example, we had a database and we've throttled it to be queried 3 times at the one time at maximum. If you have a database connection, which is some kind of state, so it's better to wrap it in an actor. So for that, you can use this util pool class to create a pool of actors. In this case of 2 actors representing the 2 different database connections. And we again reuse just the data local variable, which is just an array of some values to simulate it. And then if we have 4 futures, which will be asking the database, which is a way how you can send messages to the actor. And if you ask a message to the actor, it will give you back a future, which will be fulfilled with the answer from inside the actor. So it's basically, this also throttles the concurrency around the database because there are only 2 actors inside the pool, so it can really evaluate only 2 at any given time. There is also new implementation of channels, which works well with the promises, just a different abstraction inspired by Go. And this implementation has 2 basic operations, if you are popping a message from it or pushing a message from it, but this implementation represents this as futures. So it doesn't have really any blocking calls, which is very useful to be able to build some processing with Backpressure, but I'll be talking about that a little bit more later. So if we have a channel with a capacity of 1, and we push 2 messages into it, only the first one, the first future representing the push into the channel, will get fulfilled, and the second one will remain pending until there is a space for the message. So if you pop a value from the channel, then the second push fulfills as well. And as in Go, you can do selecting on the channels. So you can take 2 channels, call select channel factory method, which again gives you a future which will be fulfilled when there is a message available in one of these channels. And you get a pair of the channel where the message comes from and the message. And another useful trick with the promises with the future is that you can use them to simulate a process without actually needing a thread or fibers, which is useful because threads are limited. It's really not a good idea to create 10,000 threads in your application. Or fibers have issues because you cannot use really fibers on JRuby because on JRuby they are implemented by threads. So this works as follows. If you remember the flat method, which allows you to get a value from the inner future, the simulated process works that it flats as long as it's getting the future from inside, and when it runs into actual value, then it considers that as a final value of this execution. So for example, we have a count here which will just count until 5. So if the value which represents the state of this process is less than 5, it will create a future with incremented value and it will call itself. If the value reached 5, it will return the final result, the value. So then you can construct a future with this count method, and if you call run on it, it will run until it reaches some non-future value, and then it will terminate with the result here. So I've already mentioned backpressure a little bit. So what it is, if you have some producer of messages, some channel to communicate it through, and a receiver, and if you get into a situation where the receiver is consuming the messages slowly, not fast enough, not as fast as producer is creating them, you need some kind of way to signal from the receiver to the producer that it should slow down. So this can be easily done with the channel and these simulated processes, because the channel push and pop are futures, and if you remember, the push to the channel will get fulfilled only when the channel has space for the message. So if you have a process, this produce, it will continue on this line only when there is a space in the channel. So if it produces enough messages and the channel is full, it will wait a little bit for the receiver to catch up, and then it will continue. So the producer works as follows. It again produces just integers from 0 to 10. So when it's under 10, it will push a message to the channel, and then it will call itself again. Otherwise, it will push a final message nil to the channel to signal the receiver that this is the final value it will receive. And the receiver pops messages from the channel. It has internal state sum, and it will count just the messages together as long as it's getting some value. If the value is nil, which is the last one, it will just terminate with the result, with the sum. So at the end, if you run these two processes with the run method, you can see that the result of the receive process is 55. As I said, processes do not need threads. So in this example, I have 2,000 producers and 2,000 receivers, and they are running on a fast global executor. And on this line, you can see that they are all successfully finished, because I'm calling blocking wait method on each of them. I printed just the first 10 values from the receivers. They are different because all these receivers and producers are using the same channel. So since this is evaluated concurrently, it randomly gets different values, so the sum is not the same. Just the total sum is correct. But as you can see, I didn't need 400 threads for this. This runs on just the global fast executor, which has 8 threads. And with this, with channels and the simulated process, we could build a new actor implementation, ProcessingActor, which has advantages over the old one, that it uses the process simulation to behave as Erlang actors. So that will allow us in the future, for example, to port Erlang's OTP and don't reinvent the wheel. So the processing actor is really just a combination of the channel and the simulated process. So when you create an actor, you can call receive on the actor, which is again just some future. So after there is a value to be read from the mailbox from the actor, it will get fulfilled with that message, and you can process it further. In this case, this actor just receives one message, and then it it computes a power of 3. So if you tell a message to the actor, then you can read the final termination value of the actor. So the advantage is that you can easily model with these actors that they behave differently after each message, because they end up in the simulated process in different futures, which you would have to otherwise do with state machine. So for example, if you have an actor which receives 2 messages, so it calls the first to receive, then it chains the second to receive, then it computes the addition, and that will be the result of the actor. Because, as I said, it's just futures, so you can use just the zip method to combine two futures, which represent the receiving of the message together into a future computer addition, which simplifies it. The backpressure is not really limited to just the combination of the processes, channels, and another process. You can also use this with the processing actor, that if you have a body of some counter actor which will just sum numbers when it receives add command, and it will return result with the final count when it receives done command. So if you create the actor, act listening is a different factory method which allows you to inject a different channel. I will reuse a channel from before which has space only for 2 messages. And then there is a producer which will just push 10 messages into the channel. And again, because this tel is represented by a future, if the producer is too fast for the actor, it will just wait here until there is a space in the channel. We still have some time, so a few bonus slides. So far I didn't talk at all about error handling. So the main chaining method we usually use runs only if the future is fulfilled successfully. If there is an error, the then just propagates the rejection further. So in this case, if you have fulfilled future with object and you try to call succession on it, it will just fail with method undefined. So it will propagate the second succession will propagate the rejection further. There is also another chain method which allows you to call the task always when the future is resolved. So either when it's fulfilled or rejected. So you can do whatever you need in this case. In this case, we pass values further down, or we add a smiley face in the end of the exception message. And if you want to rescue or deal in some way with error, you use a rescue chaining method, which gives you the rejection, the reason as an argument for this block. So you can convert it to whatever you need, or insert some default value or whatever. In this case, we will just take the message from the exception. So this result of this future will be true because in the end it was rescued, so it was fulfilled successfully. And the value of this method is the message of the exception with the smiley face from the chain. I didn't mention there are 2 global pools there are 2 ThreadPools in CONCURRENT-RUBY. There is a fast executor and IO executor, but the IO executor is the default for everything, because we've considered that it's more safe for our users. And it's because you can post the blocking tasks to this IO thread pool. It's because this thread pool behaves, it starts with few threads, and when you want to run something on it and there are no threads available, it creates new ones. Because it assumes that there may be some cycles, dependency cycles between the tasks, so he always tries to create new thread to avoid deadlocks. This leads to more context switching, so it might be slower for some things. It also is a good idea to try to throttle the amount of tasks we are posting to this executor. And then there is another one which has a fixed number of threads based on how much cores you have in your processor, and that's good. That can be used only for non-blocking jobs. And because all the jobs are non-blocking, there is no danger of having a deadlock on this thread pool. And one more thing, I've always constructed everything through the promises module from the concurrent promises module. This is actually implementing that there is a factory methods module, which you can include anywhere you like into classes and wherever you want and need to create the futures. So for example, if you include it into this class, you can just construct the events or futures very easily by calling the methods directly. Or if you want to change the default executor for all your newly created futures, you can just override the default executor and your futures get a different thread pool. So to sum up, the advantages of this is that everything runs on a thread pool. You don't have to deal with threads directly. You can create much more actors, channels, processes, futures than you would otherwise could do with just threads. It's lock-free, so it's faster, supports backpressure. It doesn't force you to use just one abstraction. You can combine channels, actors, and promises together, and you can easily migrate from one Ruby to different Ruby implementation. Yeah, I also wanted to mention where you can find what. So the promises with all the core, with all the methods like delay, scheduling, zipping on the futures is going to 1.1 right now. The channels, Cancellation, Throttling, and ProcessingActor will stay probably until next release in Edge because they are younger. So I want to collect more feedback after before I can merge it to core. So to avoid any changes after the release. So thank you for your attention, and I'll be very happy to answer any of your questions.